All right, let's get started. Today, we begin our discussion of discretely braced beams, which I would argue is the more general case. I mean, continuously braced beams is a very specific case of beam design. It is the design where LB equals 0. But really, LB could be anything. So how do we handle that? Well, we have to look at what happens to beams when they buckle, how they buckle. We need to come up with a solution for it, which we are going to come up with a solution for beam buckling. Then there's going to be something really wrong with that solution. And we are going to fix that solution through the use of what are called Cb factors. Today's topic of discussion, today's example, today's homework is going to focus around that, around Cb. Okay? Because we're going to take it one step at a time. In terms of housekeeping, 5.4 is graded. 6.1 and 6.2 are being graded. 6.3 is due today. It's going to be the same pattern. I'll go ahead and tell you that on Friday, I'm not assigning a homework because LTB is not hard, but there's a lot there. So I kind of want Friday, I want to talk about LTB, talk about the capacity, let it soak in, then I'll give you a homework on it on Monday. Sound good? I got a method to my madness. Okay. In order to talk about LTB, warning, we are going to have some calculus approaching. We're going to have some differential equations approaching. I'm not going to make you do them, but I do need you to kind of follow and understand them, okay? I want to couch my discussion today with the following two derivatives. And if you understand this, I think you will generally get the problem that we are going to need to solve with Cb. Well, it would help if I didn't do that. Let's look at that one. I have the derivative of 5 times the sine of x. Okay. So I've highlighted that 5 because I want to ask you a question from Calc 1. How do I deal with that 5? How do you first learn how to deal with constants inside derivatives? They can factor them out, right? So, I'm not sure I heard what that said, but okay. So, we take the 5, we factor that out, and then we have the derivative of the sine, which is the cosine of x, right? So, what we can do is this. 5 we can do that, right? So that means we can do that here, right? We can say x to the third times the derivative of the sine. Right? We can do that there? No, why not? So, but what is different from the 5 to this? It's a variable, right? Okay. So what I'm talking about is this. Okay? When you solve differential equations, it is usually easier to deal with constant coefficients than it is variable coefficients, right? Because just from a basic derivative, once that coefficient becomes a variable, oh, then the derivative becomes a thing. We got to do the product rule. We got to do so it becomes different, okay? So the overall point is that when dealing with variable coefficients, we can't do that, okay? I want you to keep that in the back of your head because that's going to be important when we go through this derivation for buckling. Now, let's go back to bracing, and specifically I want to make sure that everybody is clear on what's going on right here. So here's a beam. It is simply supported. Let's say, for the sake of discussion, it's 30 foot long. So its length is 30 feet, but these are the LB terms, the distance between braces, right? Okay, and so if L is 30 feet, L sub B is 10 feet. Does that make sense? Okay, so to be clear, there is a difference between the length of the beam and the beam's unbraced length. Okay, now, up until now, all we've been caring about is beams where there was bracing everywhere. So really, LB was 0. Okay, and so what we know up right now is that when LB is 0, the capacity is just MP. That's what we know. But now I want to ask, well, what if we actually have a value for LB? What if LB is not continuously braced, but it's discretely braced? What is the capacity? Well, we got to talk about that, okay? Now, what ends up happening in the real world is that whenever you have a W shape that is being bent, you have the issue of buckling, the issue of stability. Because with columns, right, columns presented a stability issue, right? You had an element in compression, and at a certain point, the element was in compression, you load it, and it buckles. Well, beams buckle as well, okay? With beams, part of the beam's in compression, and it wants to buckle, and then there's part of the beam in tension, and it doesn't want to buckle. And so the beam doesn't really know what to do with that. It has a hard time figuring it out. And the only way that it can sort of resolve what's going on inside is it sort of does this whole kick out and twist thing. So it kind of looks like this. And we call that lateral torsional buckling. So the lateral torsional effect. So it's kicking out and twisting. And this is some example of what this looks like in the real world. When beams start to go LTB, it's actually kind of scary, you know, because this is a picture from a bridge in Canada, and you can see what's going on. I mean, these are some serious forces going on. The braces, the elements that are serving as the brace that defines your LB distances, those braces can see a lot of force. Okay, look at this super huge bridge girder. Kind of reminds us of the bridge we were talking about this morning, right? Look at what's going on in these braces. This is crazy, right? Just this total amount. The amount of load in here is nuts. Okay. Now, I think one of the easiest ways to kind of show you LTB is I'm going to pull up this video. I'm going to pull it on the other computer over here because I already have it kind of loaded up. All right, so here's this video, okay, and this is a test of a beam, and I kind of want y'all to watch this because I want you to see what the beam does as it's being loaded. Now, this is definitely a beam that is discretely braced. It is only braced at the end. So there's nothing preventing lateral movement to the left and right. Now, you can't see it, but we have a load being applied down. This thing is applying load. It's like the hydraulic press channel or something, and it is actually deflecting downward. But it's not moving to the left or right, okay? What happens right here, pew, it goes, right? Did everybody see that? It goes, and it kind of goes pretty quick. I mean, the load is really not increasing very much, but it's sort of undergoing this uncontrolled lateral displacement, and it's going pretty quick. And you can kind of see what it's doing. It's doing that whole kick out and twist thing, right? So this is the effect. This is what lateral torsional buckling really is. When it happens, it can happen very suddenly. I mean, all buckling phenomena tend to be pretty sudden failures, and they tend to be characterized by very large deformations and very sudden deformations. So there's some serious stuff going on that you kind of need to account for. Does everybody kind of understand the phenomenon, kind of get what's going on? Okay, so this is LTB, and this is the primary failure mode with which we have to deal with when looking at. Let me pause this. That we have to deal with when looking at discretely braced beams. Now, how do we deal with that mathematically? Okay, we're going to bring it back to Engineering 216 land. I know everybody's favorite class. And what we're going to do is we're going to talk about torsion. Okay, now torsion is the response, and what we're talking about is the relationship between applied load and resulting deformation when you twist something, right? Okay, so you take an element, you twist it, and so you apply some torque T, it's sort of a bending moment along the axis of the element, and it then rotates and undergoes some twist, okay? And so you probably remember this formula. I know it's been a while, but I have to believe you've at least seen this formula, that the rotation is TL over GJ. Or in differential equation speak, you can say it's T equals GJ over the rate of twist, okay? Now, here's something that would be interesting to look at if you go into your Engineering 216 notes. Whenever you learned torsion in this class, and I know you did, I know it was covered, you probably never dealt with a torsional problem involving a shape that wasn't circular, either a solid shaft or a pipe, okay? You never dealt with anything that was non-circular. And to be clear, in the land of engineering, we typically try and limit torsion to being applied to circular cross sections, okay? If you don't believe me, go look at any element in a car that's being twisted, right? We're talking about camshafts, we're talking about, you know, the steering column axle, you know, anything that's being twisted. Look at the actual mechanical element that's being twisted, and it's circular, okay? There is a reason for that, Okay? The reason is that circular cross-sections do not undergo what's called warping. Okay? What warping means is that if I take this circular shaft and I twist it, this face stays flat. It does not warp in and out of the plane. But I-beams, that's not the case. If I take an I-beam and I twist it, it actually deforms in and out of the plane. Okay? That's called warping. Okay? So, a more general relationship for torsion in a general cross-section would be something like this. Okay? So we say T equals GJ times the rate of twist, and then we say ECW times the third derivative. And the reason why we say it's the third derivative is because we're relating the response to shear, because the idea is to look at any one of these elements inside the cross-section, and they're undergoing sort of a shear, like they're sort of deforming, you know, like that. That's a shearing deformation. And so, you know, you have the deflection, the first derivative, the second derivative relates to moment, the third derivative relates to shear. So that's why you have a third derivative. Okay? And then what we have here, excuse me, what we have here is, so we have GJ times the derivative minus ECW times the derivative. And they both tend to form the same relationship. In other words, G is a material property, J is a cross-sectional property, minus E is a material property, that's 29,000 KSI. CW is a section property. Open up table 1-1 and you will see J's and CW's listed for I shapes. Now because of the derivatives, CW, the units are actually inches to the sixth, and they are big numbers, but it's because of the relationship of the derivative. So, but yeah, we actually don't end up using the J and we don't end up using the CW values directly. We do use the J values, but you'll see how that works here in a second. With me so far? Okay, so when we were dealing with column buckling, remember we had a differential equation we had to solve there. So let's look at column buckling. Man, that's horrible. Let's just do this. So when we were looking at column buckling, we had a differential equation. We had the second derivative of deflection, and then P over EI. And remember how we ended up solving it, and then we ended up coming up with this, that this was the load that caused buckling? Y'all remember that? Well, with beam buckling, we have three differential equations we have to consider. We have first off, just the general deflection of the beam. The beam is deflecting, so we are applying load, and it is deflecting vertically. And so that's this differential equation. I've got to believe that this is familiar. I mean, we've used this before, right? Okay. Now there's the lateral deflection. The lateral deflection is basically kind of the same thing. So with vertical, we have the second derivative of deflection is m over EI. For lateral, second derivative of deflection is m over EI, but there's a couple differences. It's lateral, so we're not talking about up and down. We're talking about left and right, so that's why we have U instead of V. The moment of inertia is different because we're deflecting this way instead of that way. And there's some trig in there because we're talking about taking the applied moment and splitting it up into its components. That's why there's the trig there. And then finally, we have the twisting, the torsion response. So what I'm getting at is, suffice it to say, it's a little bit more involved to do this derivation. I'm more than happy to go through it with you, but I don't really think it's totally necessary to go through that. But long story short, what ends up happening is you do a little bit of substitution, okay? You take these terms and you substitute it, and you get this, okay? This is a fourth order differential equation. I'm not making you solve it, but again, don't worry. This will become clear here in a little bit. So you get this fourth order differential equation, and you break out your Wolfram alpha or whatever tool that you want to use to solve your diffie-q. And basically what we're looking for is what is the moment that will cause buckling, and you actually get a very pretty expression, a very pretty plug and chug at the end of the day. And that's the answer, okay? Notice that I'm writing it in terms of LB, not L, but there's a lot of stuff in here that's actually really easy to solve. First off, we have E's and I's and G's and J's. All of those are lookups. Like, go to any I shape. All those properties are there. E is 29,000 KSI. G is a material property as well. For steel, we take it as 11,200. So it's not hard to plug and chug. But there is a very, very big problem with this derivation, okay? Remember those derivatives that I talked about at the beginning of the lecture? Remember those? And like we had the derivative of 5x squared, or sorry, the derivative of 5 times the sine and the derivative of x cubed times the sine. We said that you got to handle them differently because one's a constant, one's a variable, right? There's a really big problem with this derivation. And what I want you to do is I want you to focus on this differential equation, okay? So this is the differential equation that I just solved. So here's the diffie q, and I propose this is the answer. Now, where I see like phi to the fourth, that's a fourth derivative. That's a second derivative. That's a function, right? So that's what that is. I want to look at this, okay? In order to solve this diffie q and to come up with this nice, pretty plug-and-chug expression, what we've got to do is we've got to treat all these things as constants, okay? So does that pass the smell test? Well, what about E? Is that a constant? Yeah, that's 29,000 KSI, right? What about G? Yeah, that's a constant too. What about C, W, and J? That's a constant. What about IY? That's a constant. But what about M? That's a problem. How many bending moment diagrams have we ever seen that look like that? I mean, I'm serious. Do we ever deal with bending moment diagrams that look like that? No, they're nonlinear. They're pointy. They change, right? Moment is a variable along the span. But in order to come up with this nice, pretty equation, I had to treat moment like a constant. That's wrong, okay? Does that make sense? Moment has a gradient. Moment varies along the span. So what that means is I need to develop a means of correcting my solution to account for gradient moment. And that's where this comes in. This is what we're going to be talking about in our example today. This is what's called the moment gradient modifier. What it does is it adjusts our answer for lateral torsional buckling based on the fact that moment varies, okay? So I'm actually going to give you a sec to write all this down because this is some really important stuff. I have been teaching this class for a long time, and this is probably one of the tricky things. So I have a lecture devoted just to this, okay? So the formula is actually very easy. Here's the formula. We take 12.5 times the maximum moment divided by the following. 2.5 times the maximum moment plus 3MA plus 4MB plus 3MC. Okay? I'm going to give everybody a sec to write this down. I really want to talk about this and make sure this is simple. Oh, sorry. I actually hit the button. Okay. Okay. So a couple of things to consider when utilizing CB. Number one, when utilizing CB, we deal in factored loads. So what we're doing is we're taking the loads on the beam and factoring them. So the point loads, if they're live loads, multiply them by 1.6. If they're dead loads, multiply them by 1.2. Factor the loads, okay? Draw the shear diagram, draw the moment diagram. We get a moment diagram that looks something like this. One way of thinking of CB is it's kind of like the slope of the moment diagram. I say that very loosely because if the moment diagram was flat, CB would be 1, it wouldn't be 0, okay? Now, here's our function, and here's how it works. So we have a beam has a series of unbraced segments. So to skip ahead a little bit, this is the problem that we're going to do here in a little bit. This beam has 3 discrete segments. For each one of those segments, there is a single CB value. And I'll go ahead and tell you, each segment has a different CB value, okay? And so you compute a CB value for each one, okay? What you do is you take the segment and you split it into quarter points, okay? So you say, okay, oh, I'm going to take this segment, split it here, split it here, split it here. Split it into fourths, okay? And so along each of those fourths, you have MA, MB, MC. It does not matter which order that you go in. You could go A, B, C, or A, B, C. You could go the other way. It doesn't matter, because if you look at what you're doing to them mathematically, you're doing the same thing. So it doesn't matter which order you go in. Okay? For each segment, you need to report the quarter point moments and the maximum moment within that segment. For this example, the maximum moment just happens to be MB. Okay? That will not always be the case. Okay? But for this one, it is. The moments are taken as absolute values. You do not consider positives or negatives. They're all positive. And once you get that, plug and chug. Okay? Make sense? All right. Any questions? CB values are always greater than or equal to 1. If you're doing the math and you're getting something smaller than 1, you're doing something wrong. Okay? CB values typically range from 1 anywhere to about 2, maybe 2.25. That's pretty high. But they can be somewhere in that range. 1.5, 1.6, 1.3, these are all very reasonable values. Okay? With me so far? Okay, let's do a real one. We are going to determine CB values for this beam. Now, let's take a look at this. So I have a beam. It's 45 foot long. Okay? There are braces every 15 feet. So there's going to be 1, 2, 3 unbraced segments. And for each one of those unbraced segments, we're going to have a single CB value. So what that means is we are going to have to compute 1, 2, 3 CB values. Okay? Y'all remember that stuff we did in structural analysis where we derived moment functions, moment as a function of x? It's almost like we're going to have to do that again. I know, right? Sucks. But I made this problem a little easier for you. Okay? I have the beam, I have the distributed load, I have the support reactions right here. I'll give you a sec to draw that out. Because I'll show you, I made your life a little easier because I provided the shear and moment diagrams, because I'm such a nice guy. In fact, here's what I'm going to do. So what I did is, I'll pull that down here in a sec, but let me know when you're done writing this. I'll give you a second, I'll let you know what I did. Does everybody have this? So what I did is, if you look here, so here's the shear diagram, and this is something you're probably going to have to do on your homework assignment, but let's just recap how we do that, right? So we jump up 22.5, we jump up 22.5, we drop down, and so we drop down over 30 feet, so that's 2 times 30, that's 60. So if I'm at 22.5, I'm going to go down to negative 37.5, then I have my reaction, jumps me straight up to 30, jump down, I'm back to 0, right? Remind me, what's the slope of this line? Negative 2. So if this is 22.5, take that divided by 2, I get 11.25. 37.5 divided by 2, 18.75. So I can determine the area under the shear diagram, right? Right? And so we have lot to a little to a lot to a little, and our moment diagram looks like that. With me so far? Just bringing it back. We want an advanced structural analysis class. Wait, we have to remember all that stuff that we did in 312?
I didn't know you had to use stuff from other classes in the new class. Are you trying to tell us that the classes build on top of each other?
I thought prereq was just to make sure there wasn't a lot of people in each class.
Yeah. I thought they were just so we didn't have to see freshmen.
So we didn't have to see freshmen in here. Yeah, about that.
An exam? Are you going to provide those for us? And, or we have to do
I'm going to show you something here in a little bit. All right. To answer your question more seriously, for fundamental cases, there are some guides where CB is already computed. But there are some very real cases where you kind of need to know how to do it on your own. You're going to see some patterns in a bit, and you'll go, okay, I get it. Don't worry. So the homework that we're about to do is easier than this. Oh, maybe.
We're going to do the homework together?
No, we're not doing the homework together.
We're gonna do the exam together?
I'm suddenly thinking that I should start singing like a Mr. Rogers song or something. Okay. Is everybody with me on this? Okay. So let's go back to structural analysis. Let's do a pop quiz. How many functions are required to fully define this moment diagram? 2, right? Because remember, functions are interrupted by loads. So the first thing I want to be clear, so there's a couple things. These braces do not affect structural analysis at all. They're there. We have to account for them when we compute our CB values, but they don't affect the construction of your moment diagram. And 2, to be clear, this is the same parabola, right? Just because there's a maximum here does not mean this is not the same parabola. Okay. So let's see if we can figure out some of these functions. So if there's 2, I'm going to cut a section here and a section here. So we'll call this 1, 1 over here on the right and 2, 2 over here on the right. Now, let's see if you all remember. If I'm dealing with section 1, 1, if I cut a section there, which way should I look? Towards the right, right? The free end, less stuff to deal with. So let's deal with section 1, 1. So section 1, 1 looks like this. We have a distributed load. Two kips per foot. We have an unknown shear, an unknown moment. Remind me, what's this distance? X. We'll just call it X. We'll keep it simple. All right. What do I do with that distributed load? I collapse that into a single point load. How much is that point load? This is X over 2, right? With me so far? So we sum moments. Oh, I need to put my M right there. We sum moments at the cut. Y'all remember doing this? Oh, it's bringing it back, isn't it? So we say M, we say 2x, x over 2, nothing the other way. M equals negative x squared, right? So I can go up here and I can say that this function is m is negative x squared. If you don't believe me, what is the x value right here? Be careful. Right here. 15, right? Because this is x equals 0 moving forward. X equals 15. What's 15 squared? 225, and it's negative, so negative 225. So that should be pretty clear, right? With me so far? And so what we'll do is we'll say like x goes that way. All right. Any questions? So now what we'll do is we'll look at section 2-2. So here's the beam, and so I cut a section at 2-2. Which way should I look? To the left, right? So if I have section 2, and I look to the left, got a little bit more. We have 22.5 kips, again, at a distance of x. We have our shear moment, 2 kips per foot. We collapse that into a single 2x load, x over 2. Right? Okay. So what do? We sum moments. We have 22.5x m 2x x over 2. And we get that. What do you think? Bringing it back? It's like, oh, we have to do this stuff? This stuff's important? Yeah, it's important. It's almost like, yeah, this class is a prerequisite of structural analysis. I wonder who said that was like a necessity. It was Alejandro, that's who it was. Associate, thank you. Associate to the regional manager. Yeah, about that. All right, so this one is m is 22.5 x minus x squared. And again, x goes this way. So it's pretty easy to check. Let's do some checking. What happens if you plug in x equals 0? You get 0, right? What happens if you plug in x equals 30? What do you get? 22.5 times 30 minus 30 squared. Does that work? Can you plug that into your Casio FX115 ES Plus or similar scientific calculator? See if you get negative 225? Because you should get the same moment. So 22.5 times 30 minus 900. Does that work? There we go. And this maximum moment, we can determine that moment graphically from our shear diagram by plugging in 11.25, and we should get 126.56. So far, so good? All right, any questions about this? I know it's been a while, but any questions? Okay. Now, I'm going to be a little lazy, but let me see. Is my mouse in here? Yeah, my mouse is in here. I'm going to copy this image down because I kind of don't want to crowd. Oh, goodness. I don't want to crowd the calcs. So, all right. So we're going to take this, copy it down here. Okay. Now, here's the moment diagram, and if I recall, the problem has braces here, 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 and here, right? There's where the braces are, okay? So for each of these segments, I need a CB, okay? So what we're going to do is we're going to start off with the easiest segment, which I think the easiest segment is the one over here, okay? So what we're going to do for this segment is we're going to compute quarter point moments. So that means a moment right here a moment right here, and a moment right here. Okay? So let's see what that yields. So how do I compute that? How do I do that? All right, first off, what is this distance? 15. This is 15, so 15 over 4 is what? Was that 3.75? So what I'm going to do is I'm going to say, here's how I'm going to handle this. I'm going to say, oh goodness, MA is M at X equals 3.75 feet. MB is M at X equals 7.5 feet. MC is M at X equals, what is that, 11.25? Right? And what was this function again? It was M is negative X squared. So all we need is negative 3.75 squared, negative 7.5 squared, negative 11.25 squared. Oh, sorry, I need to go on the outside. So what do we get for these? And I'm going to draw them here on the diagram. So negative 14.06. We'll just say 2 decimal places. All right, what about the second one? And what about the third one?
126.56.
126.5. Oh. So, like that. Like that? Okay. All right. So remember, I should mention here, actually, let me wait. M max. So M max is the largest absolute value moment in the segment. What is the biggest value moment along this entire segment? Negative 220, no, not MC, it's this one. It's at the end, right? It doesn't have to be one of these three. It's just the absolute maximum moment along the entire segment. And that's M at X equals 15 feet, which is negative 225. Now to be clear, we take these as absolute values when we actually compute CB. And the way that we compute CB is as follows. So we have 2.5 M max plus 3 MA plus 4 MB plus 5 M or plus 3 MC all over 12.5 M max, all under 12.5 M max. So it's just a big old fraction. Say it again.
2.33.
2 1/3. Second? Sound good? Okay, all right. So what we're going to do now is we're going to do the remaining segment. Now, I don't know about you, I'm lazy when I'm an engineer. And to me, I like to do repetitive calculations using tools that handle repetitive calculations very well. So what tool do you think I want to use? There you go. So here's the thing. I'm going to need quarter point moments for all of these segments, right? I'm going to need quarter point moments here. And all the moments from here to here are defined using this function, right? So let's break out our trusty friend Microsoft Excel. Where'd this go? All right. So we have 0, 3.75, and that pattern needs to go, bless you, until 30, right? And so that is equals, why is it doing that? Okay, you want to be that way? Fine. I think this keyboard's done. It was a very, very cheap keyboard. The actual native one to the Surface is a lot better. 2.5 times x minus x squared, and we get that, right? Let's take that, let's collapse that to, well, here, let's do this. Let's round to 2. Let's do that, okay? Let's take this, box it up, take that, kind of shade it, copy this, put that there so that we have it. Here, I'll put it up here. Right? So now what we can do is we can use these values and we can say, all right, this is MA 70.31. This is MB 112.5. This is MC 126.56. And then I also have the endpoint moment, which is 112.5. So for this segment, what we have is MA, MB, MC, and this is MMax, right? Make sense? In that segment, that's the biggest one, right? For the middle segment, we have 112.5, 70.31. This is 0. This is negative 98.44, and that's negative 225. Does everybody see that? With me so far? So if you want, you can be very tabular about this for your remaining segments. As you can say, all right, so segment, let me see, did I label them like this on the beam? Okay, so we'll do it like this. So we'll say segment, here, let's do it like this. We'll say value. Segment 1, segment 2, we'll do MA, MB, MC, MMax, and then CB, right? So for the first segment, we have 14.06, 56.25. Oh no, I'm copying the wrong one. So we have 70.31, 112.5, 126.56, and then also 126.56. And then that CB, I think that CB ends up being 1.166. You can check me on that. And then for the final segment, we have 70.31, 0, 98 point, I think it's like 44. Yeah, 44, and 225. And then we need a computer CB. I actually don't have that one computed, so I'll have to do that one off to the side. Well, actually, I have students in front of me with Casio FX115 ES Plus or similar scientific calculators. What do we get as the CB for that second segment? And remember, to be crystal clear, anybody have an answer? 2.63. Do I have a second? Okay. So, and then I know we're running out of time. To summarize, here's the beam. Here's the load. Here's my supports. And then we were given braces here, braces here, braces here, and braces here. So the way I might report that is I might say CB is 1.17, CB is 2.63, CB is 2.33. And that's it. That's the answer. What do you think? Any questions? It's a very Excel-friendly problem. So what I've actually done is I've given you a simply supported beam with a uniformly distributed load. I'm going to have you compute CB, assuming bracing at the ends or bracing at the ends and at midspan. So it actually gives two different values. And there's a guide in the manual that will actually help you out in verifying your answer. So I'm thinking everybody should get the right answer at the end of the day. So,
Are we allowed to use Excel on the homework?
of course, you're an engineer.
If we do you want us to turn the Excel sheet in?
Yeah, if you would. So, if you would. Sound good? All right. Until Friday. Maybe then I'll have time. I'll show you how to do a square root by hand.
Hey, I don't know if you actually, well, I don't think